Yes, the conductor size can be selected based on its 90 degrees Celsius ampacity in this scenario, provided certain conditions are met. The fundamental principle governing this is that the weakest link determines the overall temperature limitation of the system. In this case, the 75 degrees Celsius rated equipment is the limiting factor at the termination point. Firstly, consider the conductor's ampacity at 90 degrees Celsius. This is the maximum current the conductor can carry without exceeding its insulation's temperature rating under specific conditions. Secondly, acknowledge the 75 degrees Celsius termination temperature rating. This is the maximum temperature the equipment's terminals can withstand without degradation or failure. Thirdly, the ambient temperature plays a crucial role. In the 30 degrees Celsius ambient location, the conductor's temperature rise due to current flow must be such that the conductor's temperature at the termination point does not exceed 75 degrees Celsius. Fourthly, even though the conductor is routed through a 40 degrees Celsius ambient location, the conductor's temperature will only be elevated if the ampacity of the conductor is exceeded and that the conductor is generating excessive heat. The conductor's ampacity can be selected based on the 90 degrees Celsius ampacity chart or table according to the NEC. However, it's crucial to perform calculations to verify that the conductor temperature at the termination point remains below 75 degrees Celsius. Several factors must be considered to ensure this. 1. The conductor's ampacity must be derated for the higher ambient temperature of 40 degrees Celsius. The National Electrical Code (NEC) provides ampacity correction factors for different ambient temperatures. This derating reduces the allowable current the conductor can carry. 2. The length of the conductor run in the 40 degrees Celsius ambient affects the overall temperature rise. A longer run will contribute to a higher temperature rise compared to a shorter run. 3. The conductor's insulation type impacts its heat dissipation characteristics. Some insulation types are better at dissipating heat than others. 4. The termination method and hardware also play a role. Poorly made terminations can create additional heat due to increased resistance. 5. Consider using the conductor's ampacity at 75 degrees Celsius from the NEC tables as a starting point. This will provide a larger margin of safety since the equipment is rated at 75 degrees Celsius. 6. When performing ampacity derating calculations, always refer to the latest edition of the NEC. The code provides detailed guidelines and tables for ampacity correction and adjustment factors. 7. Account for any other derating factors that may apply, such as conduit fill or the presence of multiple conductors in close proximity. These factors can further reduce the conductor's allowable ampacity. 8. Verify the equipment's listing and labeling. The equipment should be clearly marked with its temperature rating and any other relevant information. 9. Conduct a thorough visual inspection of the installation to ensure that all terminations are properly made and that there are no signs of overheating. 10. Consider using a temperature monitoring device to verify that the conductor temperature at the termination point remains within acceptable limits. This can provide an added layer of safety and assurance. Furthermore, it's important to understand the relationship between ampacity, temperature, and resistance. As the conductor temperature increases, its resistance also increases. This increased resistance leads to a higher voltage drop and potentially reduced performance of the connected equipment. The NEC provides guidelines for voltage drop calculations to ensure that the voltage at the equipment terminals remains within acceptable limits. In addition to ampacity derating, it may also be necessary to adjust the conductor size to compensate for voltage drop. This is particularly important for long conductor runs. The NEC provides formulas and tables for calculating voltage drop based on conductor size, length, and current. When selecting a conductor size, it's essential to consider both ampacity and voltage drop requirements. In some cases, the conductor size required to meet voltage drop requirements may be larger than the conductor size required to meet ampacity requirements. In such cases, the larger conductor size must be selected. Another important consideration is the type of load being served. Different types of loads have different current characteristics. For example, Inductive loads, such as motors, can draw high inrush currents during startup. These inrush currents can cause a significant voltage drop and potentially damage the equipment. When serving inductive loads, it's essential to select a conductor size that can handle the inrush current without excessive voltage drop. The NEC provides guidelines for sizing conductors for motor circuits, taking into account the motor's horsepower, voltage, and other characteristics. In addition to the NEC, other standards and regulations may also apply to conductor selection and installation. For example, the National Electrical Manufacturers Association (NEMA) publishes standards for electrical enclosures and equipment. These standards may specify requirements for conductor termination and spacing. It's essential to be familiar with all applicable standards and regulations when designing and installing electrical systems. Proper conductor selection and installation are critical for ensuring the safety and reliability of electrical systems. Incorrect conductor sizing can lead to overheating, insulation failure, and even fire. Therefore, it's essential to follow all applicable codes and standards and to consult with a qualified electrical engineer or electrician when necessary. To reiterate, the conductor can be selected based on the 90°C ampacity. However, several items must be confirmed. 1. You must ensure the temperature rating of the termination point. 2. You must stare ampacity for a 40°C environment. 3. You must consider the conductor length to avoid overheating. 4. You need to observe the conductors for signs of wear or damage. All of the above must be considered to make an informed decision. It is also crucial to consult the most recent edition of the National Electrical Code (NEC) and any local amendments to ensure compliance with all applicable regulations. The NEC provides specific guidelines for conductor selection, ampacity rating, and temperature limitations. Always prioritize safety and consult with a qualified electrical professional when in doubt. Furthermore, the selection of appropriate overcurrent protection devices, such as circuit breakers or fuses, is crucial for protecting the conductor and the connected equipment from overloads and short circuits. The overcurrent protection device must be sized according to the conductor's ampacity and any applicable rating factors. The NEC provides detailed guidelines for selecting overcurrent protection devices. In addition to overcurrent protection, ground fault protection may also be required depending on the application. Ground fault protection is designed to detect and interrupt ground faults which can pose a significant shock hazard. The NEC specifies when ground fault protection is required and provides guidelines for selecting appropriate ground fault protection devices. It's also important to consider the environmental conditions in which the conductor will be installed. Conductors installed in wet or corrosive environments must be specifically listed for those conditions. The NEC provides guidelines for selecting conductors for various environmental conditions. Furthermore, the installation method can also affect the conductor's ampacity. Conductors installed in conduit or cable trays may have a lower ampacity than conductors installed in free air. The NEC provides ampacity adjustment factors for different installation methods. When selecting a conductor, it's essential to consider all of these factors to ensure that the conductor is properly sized and protected. Neglecting any of these factors can lead to unsafe and unreliable electrical systems. In summary, while it's permissible to utilize the 90°C ampacity of the conductor under the conditions described, it necessitates careful consideration and adherence to NEC guidelines, encompassing ampacity adjustments, termination temperature limits, and appropriate overcurrent protection. Always consult the latest edition of the NEC and seek guidance from qualified professionals to ensure safe and compliant installation. Remember, electrical safety should always be the top priority. Furthermore, consider the long-term implications of your conductor selection. Will the load on the circuit increase in the future? If so, you may need to select a larger conductor size to accommodate the increased load. It's always better to err on the side of caution and select a conductor size that is slightly larger than what is currently required. This will provide some margin for future growth and prevent the need for costly and disruptive upgrades later on. In addition to conductor size, it's also important to consider the conductor material. Copper conductors are generally preferred over aluminum conductors due to their lower resistance and higher ampacity. However, aluminum conductors are less expensive than copper conductors. The choice of conductor material will depend on the specific application and budget constraints. If you choose to use aluminum conductors, it's essential to use connectors that are specifically designed for aluminum conductors. Aluminum conductors can corrode if they are not properly terminated. The NEC provides guidelines for terminating aluminum conductors. Another important consideration is the conductor's flexibility. Flexible conductors are easier to install and route than rigid conductors. However, flexible conductors may have a lower ampacity than rigid conductors. The choice of conductor flexibility will depend on the specific application and installation requirements. Furthermore, it is important to consider the conductor's color coding. The NEC requires that conductors be color-coded to identify their purpose. For example, the grounded conductor must be white or gray, and the equipment grounding conductor must be green or bare. Proper color coding is essential for ensuring the safety of electrical systems. In conclusion, conductor selection is a complex process that requires careful consideration of many factors. By following the guidelines in the NEC and consulting with qualified professionals, you can ensure that your electrical systems are safe, reliable, and compliant. Lastly, it is the responsibility of the designer or installer to ensure safe and code-compliant electrical installation.